fact that you can talk to people who have had some impact on your career, kind of listening to how they think, how down to earth they are, is just, great.
So hello everybody. Hope people are not sleepy now. Anybody sleepy yet? No? But don't worry, I'm not gonna make you sleep more, hopefully. We are gonna talk about something exciting, I promise. So as a starter to wake you up, what do you think this is? Is this, anybody can guess? Take a wild guess. What is this?
Simulation?
Well, that's an obvious answer. I wanted something fun. Yeah, so today we are going to talk about simulators, and then this is specifically an autonomous driving simulator in front of you. And by the way, that's one of my favorite bridges in the world, the Golden Gate Bridge. So yeah, welcome everyone to my talk on simulation. We are going to talk about how to make simulation more deterministic and make it safe and reliable for validation and testing any kind of robotic system. So when developing mission-critical software and robotics, it becomes very imperative to have a robust foundation of validation and verification. Collecting data from test runs and setting up infrastructure and logistics can take a lot of time and resources. Simulation comes to our rescue where it's a very robust alternative and it's also easily scalable. It is also very convenient in the cases where testing certain kind of scenarios would otherwise be difficult to replicate on the actual machines due to safety concerns. So today's talk, we'll be learning more about how to make simulator software more deterministic and enabling it for generating and testing thousands of scenarios that are crucial to the proper functioning of the actual machine. The machine here can range anything from a strawberry picking robot to a self-driving car like Tesla. To develop the simulation software for any production intent system, it's also very obvious that the natural language of choice would be C++, since it supports cross-platform compatibility, and it also has real-time performance. Yeah, so this was just the cues and the final answer. What is this? Then this will be the agenda for today. So I would first like to introduce you to ROS, which is short for the Robot Operating System, and it is a very widely used software framework in robotics. Then we will learn about some key concepts needed to understand the connection between simulators and ROS. We will try to identify some issues at hand with the existing approaches for simulation, which make it less deterministic, and finally, we'll come up with a proposal on how we can address those challenges. So let's first start with getting some history and background on ROS, which is very widely used in robotics development today. So it's a collection of software libraries, tools, APIs, which make the task of developing software for any complex system which has multi-sensors, multi-actuators, like a vehicle, very easy. In most cases, the use of such kind of a framework also dictates the general architectural principles of the developed software. So like, for example, it dictates if the software will be centralized or decentralized, whether it will be real-time or non-real-time. A key component of such kind of software is the middleware, which is the glue that holds together the numerous components of your system. The most basic task that a middleware performs is to provide the communications infrastructure between the software nodes in your robotic system. So you have your high-level application layer on the top. It could be anything like a perception algorithm or a control algorithm. And you have your low-level layers, which are the hardware, that is the sensors. You could have lidars, cameras, radars, anything on your robot. We need a glue between these two layers to interface with the hardware and get the data from the sensors and efficiently pass it on to the application to use it and provide some decision-making power to the robot. So that is what the middleware is used for. So a little bit history on ROS. It was originally developed in 2007 at the Stanford AI laboratory, and it's now being kind of managed by an organization called OSRF, which is the Open Source Robotic Foundation. Like I said before, ROS is being very widely used these days in academia, in industry, across different applications for drones, for farming, for autonomous driving. It's very easy to use, very easy to get to prototyping and then production. So it has a huge community and huge developer support. It's completely open source right now. Before we move on, I would like to tell you about basic concepts of ROS communication, which will be enabling us to understand some of the content further in the presentation. So this is a very generic example of any kind of ROS-based application system, where let's say I have taken an autonomous driving car, and it has a LiDAR sensor mounted on the top of it. And we want to read the data from that sensor to perceive the environment around us. Like if there are pedestrians in front of the car, if there are other vehicles around the car, all that data can be gathered from the sensors. So here, in the case of the vehicle, we will have some kind of ROS driver node. In very plain kind of sense, a node you can say is like a software process in ROS. Node is a very common term that ROS uses to kind of define software processes running within ROS. So we have a ROS driver node, which will keep on running, and it will keep on gathering data from this car sensor. And then it publishes this data to a topic. So a topic can be anything like, you can say, a kind of identifier on your communication wire with a name. So you can say like a topic can be LiDAR data, for example. And the ROS will publish something called as a message to this topic. So a message is data structure that can hold the data type and format, various formats for sensors. In this case specifically, the message here would be some LiDAR data format, which could be a point cloud, for example. So once the ROS driver node publishes this kind of point cloud data on the topic that we defined, then it's literally on the communication wire to be picked up by anybody who can subscribe to the same topic name. So in this diagram on the right-hand side, you can see there is this ROS-based visualization tool, which is also popularly known as RViz. And it can subscribe to literally the same LiDAR data topic that the driver published. And it can get that LiDAR data and visualize that, the point cloud inside its GUI. So that's like a basic, very basic example of how between two processes, the publisher and the subscriber, the communication happens in ROS. Then we need to understand like how the ROS ties to simulator software. So here you see that we have the, like this is the video on the left is a Carla simulator, which is an open source driving simulator again. And we are running the car in the simulator. It has a LiDAR mounted on the car. So this LiDAR data from the car as it's moving through the scene is getting published in a visualization tool in ROS. So RViz, again, like I said in the previous slide. Then on the right side, you can see the relation between how ROS and the simulator will interact with each other. So the simulator software running on your developer machine or any kind of workstation will be having the capability to publish any kind of sensor data. So like you can simulate LiDARs, camera, radars, IMUs, anything, and it will be able to publish that data on a ROS topic, and your ROS-based application, which is running a perception algorithm or a control algorithm, will be able to pick up that sensor data simulated by the simulator, and it will be able to make some kind of decision based on that. So in this case, the ROS stack is taking in the sensor data and is able to provide a feedback to the simulator through some control messages to move the vehicle forward in simulation. Now we move on to what is a simulator ROS bridge. This is also a very important concept when we are talking about simulators and ROS. So here, like consider you have Carla as a simulator, or you can have another simulator like AWSim is another popular one that the AutoWare community is using, which is an open source simulator. Or you could have IPG CarMaker, that's another vendor. So there are different vendors of simulators, but the simulator software doesn't know anything about ROS. The simulator is just like, you can imagine it could be an implementation in C++, it could be implementation in Python, so it has nothing to do with ROS. But to interface the simulator with ROS, we need like a bridge entity or a middle component that can understand both sides of the coin. So the simulator bridge here is acting as a translator between your simulator as well as the ROS-based application that you want to run. So the simulator bridge interfaces with the simulator using the simulator-specific APIs. It can fetch the sensor data from the simulator, and then the bridge converts it to a ROS message, and it publishes to a ROS topic, so that the ROS-based application stack can consume it and provide some output, which again can feed back into the bridge, and finally the bridge can apply the feedback to the simulator in the form of control commands in this case. So that's the entity for the simulator bridge that is crucial for the integration of ROS with the simulators. Okay, so now we looked at the tools to develop simulation and test scenarios, but then like what is missing? We have all the tools, right? So what is missing from this setup is that will make us feel more safe and confident in the proper functioning of the actual machine will be determinism. So unless we are confident that across, let's say, 2 different runs of the same simulation, we'll get the same kind of output from the ROS stack, we cannot be sure that my scenario that I'm testing with the simulator will work correctly on the actual machine. So I need to make certain that it's like deterministic in terms of its nature to give the same output when I am giving it the same input from the simulator. So this is the motivation for the next section of my talk, where I will touch upon first what is meant by determinism, and then we'll also see determinism in the context of simulation. So when people talk about determinism, it's like a buzzword, but there can be many interpretations that people can associate with determinism. So it's really important to understand the difference between what we are labeling as deterministic in our software system. Let's take a look. Let's say we have a scenario where a robot has to assist a surgeon for a surgery. So it's a robotic assisted surgery, for example, and the robot's arms are controlled by the surgeon who is operating on a console. So the robot must execute the surgeon's movements in real time and with very accurate precision. Any delays or jitters in the robot's response could lead to unintended movements or even damage to the tissues. This would be the case where we would need time determinism. So what time determinism tells us is when we are doing any computation in the system, then the computation should always be finished within a given time budget or a given deadline. So let's say you want to compute the robot's movement to do the surgery. If you have a time budget that the robot should perform the maneuver within 10 milliseconds, the time determinism here would be that the robot performs the maneuver in 10 milliseconds and not exceeds that. Then another kind of determinism we can talk about is data determinism, where each time you do a computation, the results of the computation are directly dependent on the input state and the input data that you have given to the system. So for the same kind of input state and input data, every time you run your system, you should expect to get the same kind of output if it's a data deterministic system. In this particular talk on simulation, I will be focusing on talking about data determinism, how can we achieve that, and two of the main pillars of data determinism would be deterministic execution, where we will ensure that given a system of ROS nodes, for example, or processes, if you will, the computations in that system will always run in the same order. So that is the condition number one for data determinism. Then condition number two is deterministic communication. So the deterministic communication concept tells us that when data is going from process A to process B in a system, then communication is guaranteed to be complete always before B executes or always after B executes. So that means that, let's say B is waiting on some kind of data from A. A publishes some data, B subscribes to it. Until and unless B gets all the data it needs to execute, B will not start executing. So that's one condition. The other scenario would be that B has already executed and then any new data can come in the system. So we will always have a known state in our system in this case. So that's the second condition to achieve data determinism. There are like other constraints that we can have for data determinism, like our system should not use any external library calls or system interfaces which are not within our execution workflow. For example, like a random number generator or a clock that can influence the output of the final computation. So now we looked at like what is determinism, what it means by determinism. Then why do we need it? What benefits can we get when we have a deterministic system? There can be numerous benefits for introducing determinism, which can help us build a safe and reliable system. Here I have listed few of them relevant for simulation and testing and validation. So the first one here is we will be able to catch early functional bugs before testing the actual application in the car. So let's say you are trying to test your self-driving stack for an unprotected left turn. Let's say this is a hypothetical scenario. I don't want to test it directly on my car, but first I would run my simulator, and then I would do like maybe tens or hundreds of runs of the same simulation scenario of the unprotected left turn on my simulation. And I would be able to determine across those multiple runs of the same scenario if each run was deterministic and would be producing the same output, then I would easily be able to catch any kind of bugs or error-prone functionality in that scenario, even before going to my actual machine. The second advantage here is you can run your entire application under constrained resources. So for an actual self-driving application, for example, you would need like a very beefed up system of CPU and memory to run it like nicely. But with determinism, you don't have the constraint of time, so you can run your whole application in very constrained manner, which can be your developer workstation, for example. Yeah, so the third one is reproducing a functional bug observed in the car. So for example, let's say you are testing your self-driving stack on the car in the field, and you observed an actual bug in the functioning of the algorithm, let's say the control algorithm. So what can be done in the case of determinism? You record that data in the field, or the whole sequence of events that led to that malfunctioning, and then you bring back that data to your developer workstation, and then you replay that data, and you can run your algorithm through it and be able to debug and fix the bug in the algorithm with it. Then there are some other advantages, like running an application in a SIL fashion, so like software in the loop fashion, where based on event-driven approach, when you are receiving or sending data, you have to trigger some execution condition, or when a timer expired, your system has to do something. So those kind of events can also be easily kind of replicated with determinism. Okay, so now we'll see some why the open source ROS is not suitable for determinism, and what we can do to make it more deterministic. So these are some of the fallacies that are there in the open source ROS, because it has not been actively tested against any production grade ECUs or any kind of RTOSs very heavily. So there are still some gaps that need to be filled to make it deterministic. One example of that is the memory allocation. When you are running your application in a mission critical software, you always need to make sure that the allocations should not happen during runtime, because you always run the risk of running out of memory. If your application demands some memory at runtime and you don't have memory, then the application will go into an undefined state, which is not good for a real-time system. And then your standard STL constructs like std string, vector, and your containers for STL, they all use usually the heap usage, which is also not recommended for a deterministic system. Another aspect is the blocking calls. So you should not have blocking calls in your system, because then again you run the risk of letting your system run into an undeterministic state, always waiting for something, and you don't know when the system will transition to the next state. So that's also something not good for determinism. So we want to overcome these challenges now that are there with open source ROS with some remedies. So these are some of the things that we can do to overcome the challenges for deterministic execution. We can allow memory allocation only during the initialization phase. So you can have like static memory allocators in your application, which can determine that, okay, like let's say we have a LiDAR that we want to process. So we can determine what will be the maximum size of the point cloud at one given point in time that it should hold in memory. And based on that, we can have certain kind of bounded data structures in our application that can be initialized to that size beforehand. We can provide memory allocator libraries for the STL data structures to make them statically allocated. We can provide set of APIs for RTOS specific properties, like we can set CPU priorities, we can set thread affinities, we can do scheduling priorities. So these kind of things will make sure that my system will always have enough resources to run the application. We can also provide synchronization primitives in our application, which will be preemptive and have scheduling priorities set. So these are some of the ways we can overcome the kind of unreadiness of ROS to not be deterministic. Yeah, so we talked generally about now what is determinism and how the deficiencies are there that we can overcome in ROS for determinism. Now we will see determinism in the context of simulation. So as I mentioned before, for data determinism, it refers to the ability to produce the same simulation result given the same set of initial conditions and initial inputs. So that is the same idea that we'll take here for the simulator determinism. We'll take an example of testing and validation of perception algorithm that will detect pedestrians in front of the car. So let's say you have this kind of example where you have some camera sensor mounted on your vehicle in the simulator, and you have some current image of the scene coming in from the simulator to your ROS stack through the ROS bridge. And your ROS stack will be running a perception algorithm that will tell you where are the pedestrians in your camera image. So we ran simulation run 1 with the first image, and we saw that it detected 2 pedestrians for us, pedestrian A, pedestrian B. Now we run the same simulation with the same ego vehicle and the same sensor setup, and in a deterministic simulation environment, we should be able to get the same 2 pedestrians detected again, and then so on. So this is like the concept of data determinism with respect to simulation, and this is like helpful for us in achieving reproducible testing of different scenarios. There are certain concepts that we need to be familiar with when implementing determinism in simulators with ROS. So one of the primary things that come with simulators is a time step sync functionality of the simulators. So with this kind of functionality, we can ensure that the simulator always runs in a controlled manner. So the time step synchronization, it's one of the more common ways to do this. It will ensure that all your simulation entities, sensors, the vehicles, the traffic participants, any other objects in your scene, it will ensure that these advance their states only once within a time step and not more. So that will be how we will control the simulator software for determinism. Then the other screw we have to tighten is on the ROS-based application side. We also need to make sure that the simulator is running in a time step sync mode, and the ROS-based application stack is kind of responding to that, and it's also only processing data when one time step has passed, and it's not like free running all the time. And third is the input consistency. So this is a crucial requirement for determinism, where inputs to the simulation, like the vehicle setup, the vehicle configurations, traffic conditions, all this initialization needs to be consistent across multiple runs. So these are some of the different possible configurations that we can have when we are dealing with simulator and the ROS-based application stack. So you have the synchronous mode in the simulator, which will increment the simulation one by one. And the ROS application mode in this case will be as fast as possible. So the ROS application stack is trying to ingest the data coming in from the simulator. As it's coming in, it's not like stopping for any kind of time step. In this case, the system will not be fully deterministic. Then the other case can be both are free running. So we don't have any control over the simulation running on the simulator, and we also don't have any control over the ROS stack that is consuming the data. So here we cannot guarantee that anything will be deterministic. Then this is the ideal case where you have the time step sync of the simulator mode, and the ROS application stack is also being controlled to run in a deterministic fashion. So in this case, the whole setup will be considered to be fully deterministic, where the ROS application only runs when the next message is gotten from the simulator on the next time step, and not before that. The last case is not adding any value for us, where we are letting the simulator run in a free fashion, but we are only controlling the ROS side of things. So it will not be a useful mode for us, as we'll always have data available, but the ROS side of things will not ingest the data as it becomes available. Okay, so we have now understood about determinism, and then in context of simulation, what determinism means. Now, I want to talk a bit about how at Apex we see this determinism concept, and we have generated some building blocks in C++, which can help us achieve determinism in a robotic system. First, I would like to tell you a little bit about our product called Apex Grace. That's our main product. So Apex Grace is a safety certified fork of ROS 2, and it has been certified up to ASIL-D with safety element out of context. So it's providing first-class C and C++ APIs for application developers that are compatible with ROS 2. It acts as a SDK for achieving real-time autonomous mobility. Specifically for this talk, from Apex Grace side, we'll be focusing on two major building blocks that we wrote in C++ that can help us achieve determinism. The first is the executor management framework, and the second is based on the executor management framework, the fixed order execution coordinator. So first I will start with defining an executor. So this is a concept which I have also seen in my experience. Many of our customers who use Apex Grace are confused about whether like is executor a scheduler or it's like different than a scheduler or what it is. So I want to also kind of differentiate here for that purpose, the difference between the scheduler in an operating system and the executor that we built. The scheduler, as you know, in an operating system is entity that assigns the work to the CPU. So in this diagram on the right side, you can see there are different kind of states, ready, running, and blocked. The scheduler will pick up any kind of thread or process that is in the ready state, and it will send it for execution, or it will send it for running. So the scheduler, based on the scheduling priorities set for the thread or thread priorities, will be able to make the decision to send a thread from ready to running. So that's the job of the scheduler. Now, the executor that we developed is not part of the operating system, but it's rather part of the framework like ROS 2 or Apex Grace. The executor's work is to define the work for the scheduler. So in this case, if you see between the running and blocked state, we have a wait for event trigger. So that means that the executor will kind of control which events will come in the system and unblock the thread which has to execute. Once it has the events that will unblock the thread that have to be executed, then the thread will be sent from the block to the ready state, and the scheduler can pick it up to run it. So the executor's focus is mainly between the running and the ready state here, if you see on the loop. So that's the difference between the scheduler and the executor entities. As part of the executor, there are like different components of the executor that we wrote in the framework, which I'll just briefly go over. So there is a concept of executable item. You can see this executable item as a node or like a class, which will define what kind of execution logic will be there once a thread is scheduled to execute. The triggering event is another entity which will tell your executor what kind of event will happen when you have to trigger your execution for the thread. So this triggering event can be taking the form of a timer where you say like, I want my thread to run every 10 milliseconds. So that could be a timer triggered event. You could make it data driven. So you could say that when I get the data from this sensor or this topic, then trigger my execution. You could have like a ROS service trigger it. You could have any kind of raw data like a UDP packet coming on a file descriptor trigger the thread for execution. So there can be different triggering events based on your choice. Then we have execution task, which combines the above two in a bundle. So it combines the executable item, which defines the execution logic, and the triggering event together into a bundle. So that's the execution task. And the executor is the main entity which controls the execution of the items of a task. And it can use one thread or parallel threads to execute the tasks. So these are the main entities we have defined in the executor framework. So this is a basic example of how you can use the executor once you have the APIs and the library. So on the first line you see you have a class mySimpleNode, which is extending from the Apex executor Apex node base. So this mySimpleNode is directly mapped to the executable item in this figure. So this will provide an entry point for execution, and it will tell you what kind of execution logic runs once your execution conditions have been met. In this class, you see number one is the execute_impl method, which contains the actual execution logic. So it can be anything from perception algorithm or a control algorithm, anything that you want to do with your data once you have your event condition satisfied. And the other method you would want to override in this class is the get triggering subscription simple. Since we are dealing with the ROS-like system here, we have named it to be triggering subscriptions, but we can also use file descriptors or timers, as I said, as triggering events instead of the subscriptions. Then the bottom part of the code from the executor setup main, that would go in your main file, in your executable file, where you can simply define your executable item from the class that you defined above. And then you can create an instance of the executor. Once you create the instance of the executor, you would need to add the executable item that the executor wants to execute to it with the executor add API. And then finally, you would want to run the executor so that it can start reacting to any triggering events that you have configured. In this case, any kind of subscription on any topic, for example. This is a sample implementation of the execute_impl method of the mySimpleNode class. So here you can see that you can define your execution logic that has to run. For example, here we are taking the messages that came in on our subscription using the take APIs. This is similar to how we take any kind of message from the communication queue in ROS. And once you take the data that came on the communication wire, you are free to do anything with it. So this myAlgo function is for, it's just a sample API which you can implement in your code to do any kind of meaningful work on the data that came in. And finally, publish is the method where you will be publishing the outcome of your algorithm in the form of a ROS message. So that's just very, very basic, very simple implementation of how some execution logic would look like within the executable item class. So now we have understood the basic entities involved in executor and how we use executor in our application. So one of the main benefits of the executor comes when you are able to achieve fixed order execution using the executor APIs. And this is really imperative for the simulation use case. So here we'll talk about two different kinds of executions. One is the uncontrolled order of execution, and another is fixed order of execution. So in the uncontrolled order of execution, you don't have any kind of control over how your system is getting executed. It could be like a live execution, it could be a simulated execution, or you could replay recorded data, for example, in a ROS bag. But you don't necessarily know that between two different runs, you would get the same kind of ordering. It's not guaranteed here. In the fixed order execution though, you should be able to be guaranteed that the execution order is always the same. So the major limitation though for the fixed order execution is, like if I give you an example, so when I told you about debugging a scenario from the actual car, you record that actual scenario that happened in the car and you bring it back to your developer laptop. For the fixed order execution, it is not guaranteed that when you replay that set of recorded data, it will be the same sequence that you recorded, that it actually happened on the car. So the fixed order execution just chooses like a arbitrary fixed order, and it will execute it in that arbitrary fixed order every time you run that data. But it's not guaranteed to be the same as it happened on the car. So that's one limitation that fixed order execution has right now. But it's still like helpful in reproducing tests of the functional behavior of an application in a given order. So this is an example of what happens with an uncontrolled order execution. So imagine you have this kind of a simulator bridge, which I talked about earlier, which is sending some data from the simulator on two topics, topic A, topic B, and two ROS nodes are consuming it. So node A is consuming the data of topic A, and node B is consuming the data of topic B. They are doing some kind of computation, and then they are publishing the result of that computation on another topic. So in this case, topic CA and topic CB. And finally, node C is consuming that data and doing something meaningful with it and publishes the final result. So we'll see now what is the effect of an uncontrolled execution while running the same setup 2 times. In this case, if you see, so here you have topic A, and at topic A, the message came which had initial integer value of 0. So A's computation logic says that increment the message value by 10 and publish it. So we'll do 0 plus 10, and then A will publish 10. Then another message came in with initial value 1, and that message came in on topic B. Topic B has to increment the message value by 100 and publish the result. So in this case, since the initial value was 1, B will publish 101. When A published the message 10, then its node C's callback A also got triggered, because node C was waiting for any data to come in on topic CA. So as soon as A published 10, node C's callback for 8 got triggered, and it stored the latest value of the message A, which is 10, in CA. So now what happens is another message came in, let's say on topic B, and it was of initial value 2. So B will publish 102. Before that though, B already published 101. So from here it got 10, and from here it got 101. So C will add the value of both message A and message B, and it will publish a result of 111. So that's like a single execution, which is not controlled by any ordering. Now we'll see what happens when we run the same setup a second time. So when you run the same setup a second time, this time, since it's not deterministic, A took a longer time to publish the message on topic CA. B already published its message, and the callback for B was triggered before the callback for A. So in this case, you see that the published result from the node C will be 101 instead of 111. So that means for the same setup across 2 different runs, we are not able to get the same output. So this system is not deterministic. And if you had a test for this, like to assert on the value of node C, the test would like fail for you. So it would be a flaky test. Before going to fixed order execution, I would like to explain the concept of like the possibilities that we have for remediating this situation. So like you saw that in any system, it's not trivial to control the execution order, the threads within a single process. So the execution of any application can take a varied amount of time if you run it multiple times. To improve upon this, we could have two possibilities. The first one is like, I could write my own scheduler to make sure that the execution order doesn't change. Like I could write my own scheduler which always schedules process A to run before process B. But this is not a friendly approach for cross-platform runs, which is very common in robotics, because as you change your platform, your scheduler and scheduling properties will change, and this would affect your scheduler. Then another option you can take to remediate the situation is writing your own management framework for execution, which is not dependent on how threads are being scheduled. So that's the approach we have also taken, where we implemented our own fixed order execution framework in C++. And there is like a coordinator entity that controls the execution order and makes sure that at one given point in time, only a single user thread will be in the executing state in the system, and not more. So if I go back to fixing this situation here, what you see now is we have this green entity called the fixed order execution coordinator, which will kind of orchestrate the execution of A and B in the system. So we'll see how. So in this example now, let's say the bridge is publishing this message, which is initial value 0. Then when the bridge publishes this message, what will happen is the coordinator will know that data is available on the system for node A to execute. Once the coordinator knows that, it will send a command to node A that please execute now, data is available for you. Then A will publish 10 in this case after computing from the message. And it will also signal back to the coordinator that I have finished executing. Now you can schedule any other node you want in the system to run after me. So then the coordinator knows that A finished executing, it published whatever it had to, and then it will then tell node C that to node C that there is a data available on your topic CA from node A. So now you can do your execution. Then node C will do its execution and store 10. Similarly, it will then send the acknowledgement back to the coordinator saying that I have finished executing, and you can now proceed with other components execution in the system. So then the bridge publishes another message, now with initial value 1. And this time it publishes on the topic B. So the coordinator takes the same kind of scheme where it will know that data is available for B to start executing. So it will send the command to B to execute. B executes. B acknowledges it has finished execution. Then the coordinator again sends the command to node C to execute based on B's output. And then C will finally publish 111. So if you run this if you run this with the coordinator again, this same message scheme, you will always be guaranteed to have 111 always. So that's like how we fix the output of the system with determinism. Okay, so this is just some implementation details for how we are achieving the fixed order execution. You saw the generic executor API before. For the fixed order execution, we have a specialized version of the executor, which is called the fixed order executor. And in this case, you will have to define the fixed order executor when you are defining that in your main executable instead of the generic executor. And you'll also need to define a timer queue proxy, which takes care of any kind of timer events in your application, and a messenger object. So this messenger object is actually responsible for coordinating the communication between your coordinator that I just showed you, and then the fixed order executor to kind of orchestrate like which execution has finished, which has not, when the data is available. So all that messaging is being done between the executor and the coordinator by the messenger object. So yeah, this is just like a flow diagram of what I explained earlier, where you have this fixed order execution coordinator in the center as a controlling entity. And we wait for the initial message or data or a timer expiration. Once that event happens, then we check if the data arrived on a triggering topic or not. If it did, then the node waits for the executor to signal that please start executing. You start executing, and then it sees if the execution condition is fulfilled, if there's any additional execution condition. And if the condition is fulfilled, then it executes the logic defined within the node, and it publishes any output data, and then again waits for, goes back to waiting for new data or new timer expiration. So this is the kind of workflow we have with the execution coordinator for fixed order. Yeah, this is the same concept, but for the simulator. So in our case, for the simulator bridge, the simulator bridge will be controlled by the coordinator to enable determinism. The coordinator will tell the simulator bridge that please send me the topic of the next message you want to publish to the ROS stack, and then the simulator bridge publishes the, let's say, a LiDAR message, and then the ROS stack consumes it. The ROS stack completes any kind of computation it wants, for example, let's say detecting pedestrians or kind of signaling any control commands back to the vehicle. So once that execution cycle is completed by the ROS stack, it will send an acknowledgement to the coordinator that I have finished executing on the data that was sent by the bridge. So please signal the bridge to send me the next set of data from the sensor. So that will, then the coordinator will again inform the bridge that we have finished one execution cycle, so you can now send the next message to the ROS stack. So this is how it will function in the case of simulator. This is something that we are currently doing at Apex, where we have integrated the Carla simulator with our Apex Grace product. And we are also right now integrating this simulator application with the coordinator interface that I just showed you. So this is like a sample operation of how things will work in Carla. There are few specific terms related to Carla that I can quickly explain to you. So this snapshot is like a snapshot of the, you can say like a current scene that you see in the simulator. That's called like a snapshot in Carla. So first, the ROS bridge will get the latest snapshot of the latest time step from the Carla server. Once it gets the latest time step, then it will update all the sensor data from that time step. So it could be any sensors added to your vehicle, like LiDAR, cameras, whatever sensors were there in that scene. It would get the data for those and update the sensor objects in the bridge. Then it will the execution will be triggered by the coordinator. So the coordinator will then loop over all the sensor objects that were captured in that particular time step, and then it will start telling the bridge to send the messages one by one. In our case, the ROS application stack is a LiDAR stack. So what it does is, when the LiDAR sensor data gets published from the ROS bridge, the LiDAR stack will compute bounding boxes of the objects it sees around the car in the simulation. So it will compute the clusters of the bounding boxes in the scene, and then it sends back the bounding box locations. Plus, it also sends back the next control commands that the vehicle has to take and run in the simulation. So when it sends back the control commands, then the bridge will again know, based on the coordinator, that one execution cycle of my ROS computation was completed for the message that I sent out. And I can send back this control command that came from my ROS stack to the simulator and advance the simulation by the next time step so that I can now get the next LiDAR data for the next time step and do the same cycle all over again. So this is the kind of deterministic workflow that we will follow if you integrate the Carla simulator with our coordinator and the executors. Yeah. So that's it. Think for me. Any questions?
Really good talk. Had a question. Sometimes ROS, like how does your the Apex Grace or whatever, does it work across the distributed systems as well? If I had, like I don't know how your fixed order execution coordinator does it. Do you have any suggestions for
how to make it work across distributed systems? Yeah, I mean, we would need like some kind of central ECU, I think. Like if you have a bunch of ECUs in your system, we would need some kind of a central ECU where we put the coordinator entity, and then it would have to then coordinate with all the, I am assuming the other ECUs are running some kind of ROS applications. Yeah, so then each of those applications would have to interface with that central entity because there can only be one coordinator in the system. And then once the coordinator kind of signals back to the application that data is available for you, your execution is done, then probably that execution will stop until it gets the next data, and then it can signal the next ECU's application to run, I guess.
Okay. And
yeah, but yeah, like that's a good question, I guess. We haven't tried that use case yet. That's a good one. Yeah.
Okay. Thanks.
Yeah. Okay.
So 2 questions.
Okay.
One is, how do I set up my own simulator? Say I want to get some data from an Unreal Engine, and is there like a mechanism provided in the API that could hook up the Unreal Engine very fast?
Well, there are like open source simulators like Carla I showed you. So you can just install they have the binaries that you can install and run the simulator server. They have also the client APIs that you can access through C++. So you can write like a C++ executable and use the client APIs to get the data from the simulation.
Okay.
Yeah.
Cool, thanks. The other question is, so say we have different sensors running at a different frame rate. What is the principle of the guidelines for synchronize different sensors with different?
Yeah, so this depends. So like for example, I can give you an example. Let's say we have a camera, we have a radar, we have some transform getting published. So it depends on like what kind of execution condition you want to tailor in your system. So if you want to fuse the camera and the radar data, and you don't care so much about, let's say, the transform message, so you can declare your camera and radar topics to be triggering for your executor, so that whenever even like a single message comes on the camera or the radar, your execution condition is met, and you can take then the latest available transform message. You don't need to necessarily wait for like store the transform message. So then you just take the transform message which is latest available and then like fuse them. So it depends on how you want to trigger your execution condition. So yes, like the sensors can definitely be of different frequencies. It's not kind of guaranteed that they'll be of same frequencies.
So meaning dropping data,
you could drop the data, in that case, yeah.
Thank you very much. Thank you for the talk.
All right.
Hi, thanks for the great talk. My question to you is, with this executor framework,
right,
can we achieve determinism at the CPU affinity level for different threads? especially to improve cache performance when your multiple nodes are processing like really large kinds of messages like point clouds or images.
So like with the deterministic execution coordinator, like that's one thing. Like that is a constraint that only one point in time it will only let one user thread be in the ready state to be picked up by the scheduler. So I mean, it will only be able to run one executable item. That's the prerequisite for making it deterministic. So
does it also guarantee that the thread runs on the same core every time so that the cache performance is?
Yeah, I mean, we could also at that point where if you are running your application on a, let's say, ROS, then you could set the, we provide some APIs where you can set the CPU and thread priorities to run your application on. So that can definitely be pinned to a particular CPU core, yeah, in that case.
Understood, thank you.
Okay.
That was a wonderful talk.
Thank you.
I missed, was there a GitHub URL for any of this work?
Sorry, you're not audible. Can you please repeat again?
Was there a GitHub URL for any of this work?
So actually the things that I presented today, everything is like our proprietary implementation. So right now we are only shipping it to customers, but maybe in the future we could consider like open sourcing some of the stuff.
Okay. Is the executor and the coordinator, are those kind of like Boost ASIO drop-in replacements for their executors, or is that something that's completely different?
No, this is completely different. So this is on the, I would say like on the DDS. So in ROS2 you have DDS, right? So these kind of things are based on the DDS weight set functionality, where it's like kind of functioning at the DDS level. So the weight set is actually an entity where you get the events in your user thread, and then the DDS weight set evaluates if your events will be triggering for the thread or not. So it's all based on the DDS weight set. So we don't have anything to do with like Boost async IO here.
Last question. Does it look like the performance of the entire stack when you're using this coordinator, does it look like a single thread, or do you still have some parallelism when you've got multiple threads and multiple cores?
No, so the rest of the application will be frozen when we are running with the coordinator. So that's the whole point of like making things more deterministic, that even though if something is running in the background, like it wouldn't be affecting the execution, like, but then we make sure that the application will be frozen. Only one user thread will be scheduled to run.
Even if it's running across multiple processes?
Yeah, that's a good one. I don't know, not sure about that one. Yeah.
All right,
yeah.
Thank you.
Okay.